Welcome to Temple of Pwn Part 7. This week we're going to go over some more heap and continue the ball rolling and talk about Fastbin dupes. So it's kind of like the T-Cash one I mentioned a couple weeks ago, probably a couple months ago at this point, I guess. But it'll just be kind of looking at the Fastbin side of things instead of more modern, I guess. Or, yeah, whatever. So again, some information on Fastbins. I've kind of went over all this before. It's a set of like a small set of bins, usually between the range 0x20, 0x80, linked to list with each other when you free them. It's similar to Tcash, where if you can control the forward pointer of the first freed one or any freed one, you can kind of control the next malloc. Depending on the libc, there might be different security checks where the previous chunk needs to be actually a real chunk, or the next chunk needs to look like a valid chunk, and kind of just those. And then the other thing I want to talk about quick is like some libc lookup. Is sometimes you might have a leak, but you don't actually know what libc you're working with. For this challenge, I'll kind of hint or like be right there in the same directory of what libc we have, but we're going to act like we don't actually know. So we'll kind of actually look up with a potential leak and see what we're actually working with. And this is the site I use, just libc.bluecat.me. All you really need is 3 nibbles of a leak. So right here, 690, the hex of that was is an address for puts, and it says this is what your libc probably is. And then from there you can go find other offsets or just download them. That's kind of all I had for slides. I was just going to go straight into the challenge, really. So what we're working with is Hack the Box's Dream Diary Chapter 1. It retired a couple months ago or something, I think. So we're able to actually go through a walkthrough of it and talk about it openly. So we'll kind of just go straight into the program, and you can see that we have sets the buffers. Going to check this function. It looks like it's just a menu that it's looping, or will come back to every time. So we'll name that. We have 4 options. We have read A to I. Looks like if it's equal to 2, it goes here. We can come in here. We can check to see it asks for the index. It says no UAF. As for data, kind of looking around, it kind of looks like it's probably since it checks to make sure a chunk is actually there, and you can kind of write something to it, which this one looks like just a read wrapper, because it's just only calling read, so we'll just call that read wrapper. But we can just assume that this is probably an edit function. Next, if it's equal to 1, we'll come to this one. Looks like we ask for a size. Mallocs it, so this is probably a allocate function or a create. Malloc error, then ask for the data, read wrapper again. Okay, so we'll just call it create. And then lastly, you probably guess what it is now. It's probably a delete, but we'll just check to make sure. And yeah, we can see that there's a free, and we can just call this one delete. So that was just a quick, just get in there and try and decide what your functions are, and then you can actually look deeper into them to see what they're actually doing, see if there's any exploits. So if we come in here and we look through the create, we can check to see that it's actually checking or making sure that there's not 15 allocations already done or 15 chunks, it looks like. It has to have a chunk that's empty. Size, there's no restrictions on your size, it looks like. You can malloc it. If the malloc fails, it'll crash, or not crash, it'll exit. It just stores it there, and then it does a read wrapper, but it looks like it does it based on the size. Doesn't look like there's any overflow unless there's one in read wrapper, but this just takes the number of bytes and the buffer, and yeah, doesn't look like there's anything there. So far this pretty much just looks like a generic create, write your data, nothing else. Check out delete. Grabs an index, A to I, has to be less than 15, can't be signed, so we can't go behind the allocation array or something, so maybe into the GOT. Might be a way to leak data in some challenges. Checks to make sure it's 0, so no double free, so it makes me think that they're not zeroing out, but it looks like they do zero it out, so there's no real reason to that. Then it just frees the pointer. It doesn't print anything about what's in your spot, so looks like we might not actually be able to actually print data, but we're able to create, delete, and write. So if we go into the edit, same thing as delete, can't be signed, has to be less than or equal to 15, has to be valid, and then right here it takes the string length of our data chunk, and then it'll print data and then read it into based on the string length, it looks like. So this is kind of actually where our vulnerability is based on the string length. As we saw kind of previously, open up a notepad when you, let's see if I can create something. So if you were to just put in a bunch of data, we'll just call this is what our kind of heap looks like. Then we usually, at the end, it usually has that size of the next one. So it'll be 21. Usually these will go unsigned, not unsigned, but big Indian. I think I'm off by 8, but whatever. So when you're writing data, it goes usually first byte, second byte, all the way, and it's big in, or little endian. So when you come here and you write all this one, we're able to write up to this point, and then when it does the string length, it'll also grab this one, allowing us to overwrite the size of the next chunk and make it think it's actually a different size than it actually is. And that's what we'll exploit. So here you can see that I have 2.23 downloaded, and the hint for that is that on the challenge itself it said hint Zenial Xerxes, I think. Xerxes libc. You just search that, you can see that it's 2.23. But if that hint wasn't there, we'll go over that too. Otherwise, we have the chapter 1 binary, an exploit that I wrote previously to make sure I still knew what I was doing. And then we'll just go into the copy the template to exploit. Let's actually move exploit to backup. And we'll copy template exploit.py. So inside right now I just have some default functions. So I have a send, send2. These both just will read or send your line that you send in after a character that you send in. I just like to do it this way to make it so I'm not doing p.send after all of these time after time. And then this way we can just have a create function, an edit function, and a delete function. And then we just have this interaction with GDB and pdet interactive. So what we're going to do is kind of just see what we're working with. So let's just create 2 chunks of size 24, put an A of, or 24 A's, and we'll create another one of B's. Whoops. Oh, it did keep the same size. Okay. So if we go into the heap, we can see what it looks like, and we have it right here. So how chunks are allocated is that they're on 16-byte boundaries. So if you send in, or if you want 24 characters, that's going to be 16. Here's another 8, so 24. So right now we have the 24 goes straight and what am I thinking of? It not overflows, but it concats, I guess, to the size. So if we go and edit 0 and put in, let's just say a bunch of B's. I'm not sure what the exact amount is. This might actually crash the buffer. Oh, it didn't. But if we check here now, we can see that we overwrote it because of the string length read that they were using. So what we're going to do is try and get overlapping chunks, because that's what we always want to do with a heap challenge. And then from there we can go and try and get a Fastbin Dup, because we're working with an older libc and we're able to just get that going. So to make this work, we need to know that we can only work with sizes that are less than 0x80 if we want to work with fastbins. We could make a chunk look like an unsorted bin, or larger than a fastbin, so it gets tossed in the unsorted bin, and then our next allocation could be that chunk, and that's probably the best bet we have. So for now, let's just do a couple allocations. We'll do size, I'm going to change this to 0x18, which is still 24. 8, so we have A, B, C. I think I'm going to want D also, and then I'm going to also have one more called just for barrier. You usually just want to have one allocation at the bottom, so if these weren't fast bins and they were larger bin chunks and you freed them all, they would just be consolidated with the top chunk of this piece, and you'd lose everything inside your unsorted or small bin array. So this way, if you have a barrier, you don't have to worry about that. So creating those, we can go and edit 0 to be A times 24 plus backslash. We're going to want a size of 0x40, because what we're going to do is pretty much, so this will be our first chunk, our second will be here, and our third one will be here. So what we're going to do is overwrite this size to 40, So it makes it think that this chunk is actually a size of 40, so it jumps right over the chunk of C. And we can see that if I run it again. Oh, backslash x is 0x. Nice. And here we can see that this 40, so this actually points to down here, and if we free it, it'll think it's actually that huge chunk. So if we free 1, we can check the heap bins and see that it thinks it's a size of 40. So if we allocate it, we should be able to overwrite C entirely. So 40 would be 64 minus 8 be 58. Just put in a bunch of Z's. I don't know if I put in enough. Check out this again. It doesn't look like it. Did I do the wrong size? May have done the wrong size. Let's see. 40 should be 64. Minus 8 is 56, not 58. That's why. So if we try that again, 56. Gotta continue. Well, let's try that one more time. So we should have the delete on 1, allocate a size of 56, bunch of Z's. We'll have to do VM map. And there we go. We can see that we actually overwrote into the C chunk. This is going to be useful because now if we free C, we're able to, or not free it, but if we were to free C before we allocated this chunk, we're able to kind of just control the size 20's forward pointer then. And that should be a relatively simple thing to do. So we edit first, delete 2, delete 1. So this will get the C's onto the T free Fastbin list. This will get the B spot into the Fastbin list. Will be 20, 40. Create 0x38. We'll go a bunch of Z's times 0x32 plus P64 of 0x dead beef cafe babe. So we'll go heap bins. We should see that. Oh, I must have botched it. Oh well. Wanted to get dead beef cafe babe in there. But that doesn't matter. I must have been off by. Did I do 0x32? I did. Fix that for later. Alright, but we can see that we actually control this. So, like, pretty much just like Tcache, we're able to point this wherever we kind of want and get an allocation there now. So what we do know is that I forgot to do check sec on the binary. Chapter 1. And we can see that there's no pi, and it's loaded at that address for some reason. That is a different address than it was earlier, I think. Maybe not. Yeah, it was at 400,000 earlier. Why is it like... Well then, I'm not really sure why it's at 3FE here and 400 on IDA, but let's go by it with it. So this allocation is always going to be the same at 3FE000, and then the BSS and data sections will always be in these spots too. So since this isn't full row, that means we're able to influence the GOT. So if we're able to actually get a Fastbin up here, where we can just get an infinite read or write, but there is one check with Fastbins, is that you have to have a valid previous, not previous, but valid, yeah, valid size, I guess, header. So we can't just point it straight here and overwrite our list of allocations because there's no valid size right here. We need a valid size of the same Tcache. So if we were to point it somewhere, like if we were to point it here, this would need to be the size of 0x40 because that's the chunk we're looking at right now. But we are able to do offsets. Let's go back to this spot. So like it doesn't have to be on an even 8-byte boundary or 16-byte boundary. So we could do plus 1, minus 1, I mean, minus another one right here. So if we pointed it at this address, we now have the size that makes it think it looks like 7F, which it's actually going to be like 7. I don't know if it's not really 7F because it doesn't care about the top 5 bits of the lower nibble. It only cares about the last 3 bits. So we can use that address. We'll do address equals this. Probably put it up here so we can overwrite it. Address, and then I'll just show you what it looks like. Did I leave? It did. Okay. So check out heap bins. We can see that it points there correctly. This says the size. That's going to be a problem because I'll need to fix that then. So if we try to allocate a size of 0x20, it's going to say corruption or whatever. So size 24 right there. Yep. Memory corruption. So that's one of the checks. We need to make sure the size is correct. So we can do 24 plus P64 0x. We're going to want, right now it's in 20. So just work with that. I'll change it to what we'll need in a little bit. Check out heap bins. See that this size is correct. This size is not correct because I don't think it's pointing to the right spot. Yeah, it's off by 10. It's 10. Yep, because I want it to point right here. So we'll need to actually set it to 9D instead of AD. No problem though. Change that to 90, and then we can just check to see. So we'll allocate one of size 24, ABCD. Allocate another size 24. Corruption. Oh yeah, that's because if we checked out our heap bins, that's because right now the size doesn't match up what we wanted to, because it's actually going to say it's a size of 7F or 70 with some allocation differences. So instead we'll need to use chunks of size 7. So change these all to 6. 24, we'll need to change that to 0x68. Change this to 0x68. This one to 71. So if we check out our heap bins, we should see that everything should. That doesn't line up. And we have invalid choice, so something didn't go correctly. This one. Six, 8. Alright, so that's our problem now. So I'll close that one. So when we're overwriting this, or this chunk of B, 0x6 or 0x41 doesn't work anymore, and we're going to actually need to change that to E1, I think. 7 plus 7 should be E. It doesn't look like it was. Oh, I didn't free it. Oh, yeah, I did. So let's pause these and just check to make sure that when it edits it, it's correct. And it doesn't even look anywhere near to being correct. Oh, and that's because of this. So you have to remember it's off the stream length, so if we only pass it 24 characters, it's only going to continue to let us edit 24 characters. So we need to at least pass in 0x68 to start. There we go. That should give us the, yep, okay. And then we'll just check while we're here. E, there's 7, there's another 7. Oh yeah, so that lines up right. So we should be able to delete 1, which I want to delete 2 first, but this just shows us that instead of being in the fast bin, it's actually going to be in the unsorted bin now, and we can still work with that. So now that those are good, we can delete these 2, And we should be able to create this one, because this should grab C's. And then the next thing on the... Oh, wait. No, this won't grab C's. We don't want to grab C's. We want to grab the unsorted bin one. So we might as well just do a chunk of D8. That should be large enough. And I'll take it out of the unsorted bin and put it in here. And then as we can see, it's going to say it's a size of 7/8. And this is the address we want. And it just says it's in use, is M-mapped, and is not a main arena, which is what those bottom 3 bits are for. Since it's actually a size of 8, it doesn't really matter because we're in a 64-bit system. It's still going to realize that it's only a size of 7/0 or something. So if we allocate, oh gosh, that 96, 88, I think. Oops. And I botched it. Create 0x68. We'll just put in a bunch of A's to show that we actually have writability where we want. No, we won't. Oh, I guess we will, but not yet we won't. So the next one on the top of the list should be that. So if we allocate another chunk of that size, which is I think 88, put a bunch of A's in there. Was not 88. 60 is 96. Oh, 96. So it should be 96, I guess. Off by a factor of 16. There we go. So if we go back to that address, I'm just going to come up here and copy it. We should see that now we're actually able to overwrite our allocation list, which is exactly what we want to do, because since I think number 5 points at the beginning, we're able to just continuously edit it, while we can overwrite 1, 2, 3, since there's no other checks to see if it's actually a valid heap chunk or not. We could just overwrite this to be the GOT or something, so we can just get infinite leaks or infinite writes. But you're probably thinking, but we don't have any way to actually leak it at the moment because there's no way to print what's in the heap. Okay. So what we're going to do is actually go into back to main. Not sure why this looks weird. Whatever. And what we could do is instead of inside delete, instead of free, if we overwrote the GOT entry of free with the PLT of puts, so every time free is called, puts will actually be called, and this allows us to leak anything that's at the pointer we control. So we go back, we create the next one as 0x68. A times, just put A because I'm not sure what the actual size we want is. So it looks like the first chunk is after 16. 1, 2, 3. After 3, some 19 characters. 19 plus P64 of free underscore got. So let's get that address, and then we're also going to want puts underscore PLT. So we grab, just come in here, go to free, see that it's at 4006D0. X, go to puts. That was not the right address. That was freeze PLT. We want freeze got, which is at 602.018. And then we want puts PLT. Puts, where are you at? There you are. That one's at 4006E0. So we're going to make it look like the first chunk, or the first piece now points to free got, so we can edit 0, which is the first one, with P64 of puts underscore PLT. I don't think this should cause any problems, but there could be some errors with this part because it only does the string length, and since free's got is going to point to the free address. That's actually only going to be 6 bytes. But if we do P64, it's going to be 8 bytes. So I'm just going to be safe and say we only want to write 6 bytes there. Now if we go and check with our GOT, we can see that this now points to puts PLT. And if we tried to delete a chunk, I think 4 still points to a heap. Maybe not. Whoops, that was the wrong button. Does 3 still point to a chunk? 3 points to the letters D. Oh yeah, this one is where heap's at, so if we need to... So, now we could do is something like plus P64 of free got plus 8. So we'll describe the piece or the value it's right after free got, and we're able to leak that. And we should be able to do that with delete 2 with or delete 1. Continue this, delete 1, and there we go. That's a leakable address. So if we check, that's actually the address it puts. So we can do... So this is where we can figure out our leak if we didn't actually know what libc we were working with. Because all these addresses are static and we haven't actually done anything libc-wise, you should be able to technically get this all done without needing the libc. So let's take this 690, go to libc lookup, say we want at 690, we want the address it puts, and we'll find it, and lo and behold, it's the 23 that we already have. At this point, you might want to just check both to see if any of the offsets are different. Looks like system's at 45390, and it looks like they're both the exact same, so you don't really have to care too much depending on how your exploit goes. But for us, we only want that system one, and we'll also take the puts one. So let's put this here for now, and we'll take the puts one also. Change this to plus. libc is equal to leak minus puts, minus that. So we could delete 1, that'll get us to the leak, which should look like this. So I think I should be able to read until new line. Put that after, then P to read until the new one, the next new line. Get rid of the new line character because we don't care about it, and I'll just print out what it looks like. And code a hex. These will probably crash it, but that doesn't really matter too much. Invalid the rule for base 10. What? Oh, not read until. There we go. So it looks like that is not what we want. So we have to change this quick and see what we actually get in return when we're running it. Which looks like it reads past it already. So maybe we just need to read until the first new line. Yeah. It looks like there's also a space on there, which wasn't there earlier. No worries. So we just say leak is equal to this one. Get rid of the first and the last character. Leak, that should be fine. We can do a leak is equal to u64 of leak dot l left adjust to with the character null byte. Oops. And we want it to be 8 places. So this is going to do just pad it out because u64 needs 8 characters to make sure it actually works. And we should be able to do print the hex of leak. And we should be able to get the libc and system now. The hex of system and the hex of libc. So let's check to make sure that the system is right. System and we can see that it is indeed 8A390. So what we kind of want to do now is find a way to run bin sh with our system, and the most approachable idea is probably to overwrite free and have it be that way, but the problem is that since it uses the string length and our libc address is going to be at least 6 bytes, we can't because it's down to 3 now. I think it's 6, 2, 4, 6, yeah. This one's down to 3, so we're kind of done with that idea, but if we were to overwrite string length, which is still at the... Alright, still it's the libc address, we're able to overwrite with a full 6 bytes, and if we look, string length is only called once in edit, and it's by pretty much the same way as free, but it's with our chunk. So if we can put bin sh into a chunk and then call string length on it, then we get the shell back. So we'll just come up here and just add it to the end, plus p64 free got plus 16, it's just one more after it. We can do a edit on 2 now, p64 of system with up to 6 characters, just to be safe. And then from there we should just be able to free any of them that point to it currently, which I'm just going to put bin sh here. That way 0, 1, 2, 3, 4 should point there. So when we try to edit 4, we should get a shell, and we did. So that's the way to exploit that challenge. So if you were to like try this exact method step by step, it'll probably fail on the remote server. One, because I don't think it leaks. I don't think it reads the new line the same way on the remote server. And then 2, for some reason, this challenge alone doesn't like it when you send the character 0x7f. So you either need to find a way to bypass that restriction or just brute force it until you get an offset that doesn't include 0x7f for the libc, but it's kind of usually 0x7f is kind of the default for libc, so it's usually like a 1 in, I don't think it's 256. That might be. I think it's like a 1 in 256 chance that works. But yeah, that was kind of a quick overview of this. Or is there any questions about the heap methodology of this or anything you want me to go back over?
I do have a quick question. Sorry, I came a little bit late. So, would overwriting the free hook not be an option for this scenario?
Oh, that'd be an other situation. Actually, free hook might be a little bit harder with this methodology because you're doing a Fastbin Dup. Because if we look at the free hook, we can see and just check out the address right before, because we need to have a valid size pointer, and there's no valid size pointers right before free hook until I think a good 1,000 before it. Even then there's still nothing. This one might be valid work with. I think malloc hook would be a better one to target,
Okay.
but at that point you'd still need to leak the libc, and then you pretty much already have control of the pointers and already have got, but if the got's not writable, then yeah, this would be a good way to go for it. I think, because standard out should be above it. Minus 0x100. Whatever. But memalign is there, and that's another 7f, so that'd be a valid chunk to work with too. Well, if there's nothing else, thanks for coming, everyone, and I think next week I might do the same challenge, but look at an unsafe unlink method, where we're trying to make it look like there's a valid chunk where there's not just based on size, but with valid pointers to make it kind of consolidate into a valid or an allocation in the unsorted bin instead of on the fast bins.